Acid-base, lesson number 14, calculations involving Ka. Recall that when a weak acid is put into water, the acid does not completely ionize. All weak acids undergo less than 100% ionization in aqueous solution. For example 1, what pH results when 0.50 molar hydrofluoric acid is dissolved in water? From a Bronsted-Lowry acid-base table, we can identify hydrofluoric acid as a weak acid. And being a weak acid, we can write its Bronsted-Lowry equilibrium. We're told that the molarity of the hydrofluoric acid is 0.50 molar. And we know approximately the molarity of the ions, H3O plus and F minus, would both be much less than 0.50 molar. In order to determine the pH of this hydrofluoric acid solution, we need to determine the H3O plus molarity exactly. Therefore, to solve for H3O plus, you must set up and solve an ice table. Let's go ahead and set up our ice table. We'll start with the weak acid equilibrium. Initial change in equilibrium on the left-hand side. We know the initial HF is 0.50. We'll leave out units. H3O plus and F minus initially would both be 0. Since we're starting with HF on the left-hand side, Le Chataillet's principle will shift towards the right, minus, plus, and plus. H2O is present in the Bronsted-Lowry equation, but water does not have a molarity, so it is left blank when we fill in our ice table. The mole ratio here is 1 to 1 to 1 to 1. We don't know the amount of the shift, therefore it'll be X. I plus C is equal to E. And completing our ice table, this is what we will have. Now we need to solve for X. To solve for X, we'll first set up our Ka expression. Products over reactants, omitting the pure liquid water. From our data book, we can look up the Ka for hydrofluoric acid, and we find that the Ka is equal to 3.5 times 10 to the negative 4. We'll substitute our values in from our ice table. Now, going ahead and solving this equation for X, we realize that we have an X squared term, an X term, and a constant, and this would result in a quadratic equation. We could go ahead and solve this using our quadratic formula, and we can come up with our value for X, but being a weak acid, we can simplify this knowing that the value for X is going to be extremely small. So let's go back to our ice table. If we know that the H3O plus, going back here, if we know that this number here is going to be much less than 0.50 molar, then X minus, or 0.50 minus X is going to be approximately just 0.50. If X is infinitely small, this 0.50 is not going to change very much. Therefore, if we go back to our question here, this will simplify to this equation here. We can assume that 0.50 minus X is essentially 0.50. X is going to be negligible. Now we can solve this for x quite easily and not have to deal with a quadratic equation. So let's go ahead and solve this for x. And to 2 sig figs, I get 0.013. Let's take this back to our ice table. We see that the molarity of H3O plus at equilibrium is equal to x, so we know the value here. We now can say that the H3O plus at equilibrium is 0.013 molar. And knowing this, we can determine the pH, as the formula for pH is negative log of H3O plus. Substitute our molarity in. And solving for the pH to 2 sig figs, which means 2 decimal places, we find that the pH is equal to 1.89. Therefore, the pH of a 0.50 molar solution of hydrofluoric acid would be equal to 1.89. Example 2. A 0.24 molar solution of a weak acid has a pH of 3.49. What is the Ka and identify the acid? In this case, we're told we have a weak acid, but we don't know the identity of the weak acid. So our starting point is to assign just a generic chemical formula here for the weak acid, and common abbreviations that are given are HA or HX. I'm going to use HA for this example. And using HA for our unknown weak acid, we can write our Bronsted-Lowry equilibrium, and knowing that it is a weak acid, it will exist in equilibrium. Also knowing that it is a weak acid, we can set up an ice table. We're told the initial molarity is 0.24. We're also told that the pH is equal to 3.49. So if the pH is equal to 3.49, we can turn that into the H3O plus molarity by taking the antilog of negative 3.49, and this would be equal to 3.2 times 10 to the negative 4 molar. We can bring this number into our ice table. 3.2 times 10 to the negative 4 minus plus plus. Again, it's a 1 to 1 to 1 to 1 mole ratio. 3.2 times 10 to the negative 4 right across on the change line. And doing the subtraction here, 0.24 minus 3.2 times 10 to the negative 4 would give me 0.23968, which would round to just 0.24, and this would be 3.2 times 10 to the negative 4. A generic Ka expression here, H3O plus, A minus over HA. Plug in our values here. 3.2 times 10 to the negative 4 for H3O plus. 3.2 times 10 to the negative 4 for A minus over molarity of 0.24 for HA. And solving for the Ka here, we find that the Ka will be equal to 4.3 times 10 to the negative 7. There are no units for Ka as it is a constant. Looking on our Bronsted-Lowry acid base table, we see that this matches up exactly with carbonic acid. So we've calculated the Ka and we've identified the weak acid. Our third example, what mass of ammonium nitrate will produce 5 liters of a solution having a pOH of 8.50? We'll first realize that ammonium nitrate is a salt. So we will write the dissociation of ammonium nitrate. Check for spectators and realize that NO3- is the conjugate base of a strong acid HNO3. This will be our spectator ion and will not undergo any further reactions. But NH4+ we can identify as a weak acid. And being a weak acid, we can write its Bronsted-Lowry equilibrium. We're asked, what mass of NH4NO3? So in this question here, we were asked to find the mass of the salt that's originally placed into this solution. Therefore, we need to find out the NH4+ molarity initially. There's nothing else placed into the flask initially, but we are also told that we have a pOH of 8.50. Which means that we have a pH equal to 14 minus 8.50, which will be equal to 5.50. And based on that, we can calculate the H3O+ molarity at equilibrium. It's antilog minus 5.50, which works out to 3.2 times 10 to the negative 6 molar. Let's bring this into our ice table. That would come in here. Plus, plus, minus. And now let's complete our ice table. Now with our ice table completed, let's go ahead and write our Ka expression. We can look up the Ka for the ammonium ion, and this is equal to 5.6 times 10 to the minus 10. Substitute our values in from our ice table. And now we have an equation where we can go ahead and solve for x. So let's go ahead and do the math here and solve for x. We'll cross multiply. This will be equal to 3.2 times 10 to the negative 6 squared. So 5.6 times 10 to the negative 10x minus 1.8 times 10 to the negative 15 when we distribute. This is equal to 1.0 times 10 to the negative 11 plus 1.8 times 10 to the negative 15. This would cancel, and then we'd get 5.6 times 10 to the negative 10x is equal to 1.0 times 10 to the negative 11 divided by 5.6 times 10 to the negative 10. Cancels out here, and we find that x is equal to 2 sig figs, 0.018. Therefore, going back to our ice table, we see that the molarity of the NH4 plus is equal to 0.018 molar. Now we'll take this value and we'll have to find the mass of ammonium nitrate needed in this 5-liter solution. Therefore, we can first calculate the moles of NH4 plus, which is equal to C times V, the molarity, 0.018 molar, times the volume of 5 liters. And this would be equal to 0.090 moles of NH4 plus. And now to find the mass, one mole of NH4 plus is equivalent to 1 mole of NH4NO3, and 1 mole of NH4NO3 has a mass of 80.0 grams as its molar mass. And working this out, moles NH4 plus cancel, moles NH4NO3 cancel. This will work out to 7.2 grams of NH4NO3 that would be needed to dissolve in this 5-liter flask to yield a pOH of 8.50. The Hebden assignment for this lesson is page 152, numbers 74 to 83.